Okay, good morning to everyone. I'm very glad to announce or to present Victoria Graffigna here in order to show us the works Victoria and Mauricio have done in La Plata University some time ago. The work or the presentations is entitled Analysis of Temporal Variations in Zenith Tropospheric Delay derived from GNSS observations. So we are very glad in this 8th seminar of IonSAT Research Group to have Victoria here. Victoria Graffigna is PhD student at La Plata University. Her current research focus on GNSS signal analysis and troposphere delay modeling in terms of meteorology and navigation applications. During last year, Victoria developed her master project here at IonSAT Group UPC. And that's all. I just to give the floor to Victoria. Thanks so much.
Thank you, Manuel. Well, hello, everyone. Twice the people we expected, so we're happy. As Manuel said, my name is Victoria, and I'm from Argentina. I did my undergraduate studies in La Plata, and I'm doing my PhD there as well. It's starting next month, actually. And I did my master's project in UPC with Manuel last year, and with Alberto too. And he's also my director for my PhD. So I'll be coming back and sharing my progress in research with you, hopefully. This is a work that I did almost 2 years ago. I finished 2 years ago as my undergraduate thesis. In Argentina, we do that. I don't know if here, probably you do as well. So yeah, that's it. This is the outlook. What I'm going to be talking about is the tropospheric delay. Basically, what's the troposphere, what we mean by troposphere and by tropospheric delay, what data and methodology we have used to analyze the data and the results we have obtained. So here we are only analyzing products from other centers. It's not our data. We want to know how it behaves. Okay. Our motivation is to study the relationship between the tropospheric delay that we can obtain from GPS data or GNSS data. How does it relate with the local weather? So can we estimate local weather parameters? Can we study the atmosphere? Can we predict at some point? Maybe. So does it respond to the laws of the atmospheric physics? Does it have any relationship with the pressure variations or the winds? How does it behave? Or is it totally a separate phenomena to the local weather? Is it just a random error from GPS? Or does it respond to something, to a physical phenomenon? That's the idea. Okay, so I always like to start my presentations with the definition of the troposphere, that for the meteorologists is the first 10 to 12 kilometers, and it's the first layer of the atmosphere, the lower layer, the closer to the Earth, and it responds to changes in temperature gradient. So they divide the atmosphere according to the changes in the gradient. For us, the people that do geodesy, we only have 2 layers, the troposphere and the ionosphere. So we care how the molecules or the particles in the atmosphere respond to the radiation of the sun. Do they feel the radiation or not? So if they don't, it's the neutral atmosphere, and if they do, it's the ionosphere. So that divides the atmosphere in, this is 250 kilometers. This is the first 50 kilometers is what we call the troposphere. For us, it's 5 times what it is for the meteorologists. So what is the tropospheric delay? Is the additional path or time traveled by the radio signal due to the refraction in the neutral atmosphere. So it's a time. It's the difference in time of what the radio signal would spend if it had traveled by the vacuum minus the real path, or the other way. It's the same. Since it's a distance as well, we multiply by the velocity of the wave, and using the refraction index, we can convert to distance. So this is what we call the troposphere delay, which is, it has mainly 2 components. One, due to the change in the refraction index along the path, and the other one that accounts for the difference for the bending of the path. And doing some math and using the refractivity instead of the refraction index, we can express the troposphere delay by the addition of 2 parts. One part that corresponds to the hydrostatic refraction, and the other one that is the rest. The rest is mostly the wet components of the atmosphere. That's why we write it as NW, but it's actually the rest. It's not only the water vapor. It's everything that is not in hydrostatic equilibrium. In particular, if we consider the zenithal path, we can say that we have the zenith troposphere delay, which is just considering that the signal is traveling in the zenith direction. But in general, we will express, this is how we consider it. It's the addition of 2 parts, again, considering the dry or the hydrostatic, which are called the same, and the wet part is the hydrostatic times a mapping function that is going to account for the difference of the delay in between the zenith and the real path. So it's going to multiply, it's going to make it bigger, because the zenith direction is going to be bigger. In the real direction is going to be bigger. You can stop me at any time because it's a seminar, so feel free to ask any questions at any time. So the zenith hydrostatic delay, it's easy to model because it's hydrostatic, so it responds to the hydrostatic equilibrium equations. So the only parameter we need to model is the atmosphere density or pressure, which are the same, are telling us the same. So the integral between the point of observation until the infinite, we consider that the signal has traveled, comes from the infinite. It's only a constant that depends on the pressure at the surface of the receiver. So that's fairly easy to know. So there's no problem with the hydrostatic delay. It's constant, and the only parameter we need to know at the place is the pressure at the surface. On the other hand, the zenith wet delay, we also express the refractivity coefficient. It's inside the integral. And we have some laws that, this is the Clapeyron equation, and I only put them there just to show that there is some physics supporting the system, but there is no closed formula to estimating the water vapor, which is the E in the first equation. So the temperature, we need to know the temperature, the pressure, water vapor pressure, partial pressure. And so there is no easy way to estimate this. There is an approximation to it that requires some parameters. So here it was only 1, and here we need 3. Is the mean temperature for the whole column of the zenith direction. This is how the water vapor changes with height, and this is the water vapor. Now we only need it at the surface where we are observing, but it is still not easy to know. There's no model to predict it because it's highly variable in time and space. So usually this is estimated. It is not calculated because it's not easy to know all those parameters that you need. So we're done with the math. So this is the data we have used. This is the map for all the stations in South America or Latin America. The red ones are both IGS and the regional reference system, which is called CIRGAS, which has, doesn't say here, but I think by now it has like 500 stations, permanent stations in the whole South America, but only less than 100 are also IGS stations, International Geodetic Service. So we have used from IGS and we have used data from both sources. From IGS, why? Well, because the center analysis have the better reputation than CIRGAS. They have been doing this for I think two decades. Since 1994, I think this product is available, the Zenith Troposphere Delay. And so we have used those ones as well, but it's only for 59 stations without applying any filter. So we started off with 59 stations, which is not much. So we also, we first started working only with IGS, then we realized it was not enough to analyze anything. So we added almost 400 sites from CIRGAS. The center that gave us the Zenith Troposphere Delay is located in Mendoza, and it's an experimental atmospheric center. So it's working well, and the people there are doing the things very well, but it's still not IGS. It doesn't belong to the IGS service. So with the IGS data, we filtered for South America, of course, and we asked the time series to have at least 3 years of continuous data. To analyze periods, you need continuous data and at least twice the smaller cycle you want to see. So if you want to see an annual cycle, you need at least 2 years. So we asked it for 3 years. From 59 sites, we only got 25 because the other ones didn't have 3 continuous years of data. And from CIRGAS, the longer data series was 2 years. So we decided we were not going to study the annual cycle with CIRGAS. We were only going to study the diurnal cycle. And we asked it not to have more than 30 days of missing data. After that, we filter. There's some epochs have 2, 3, or 4 values from the same epoch. So that's not coherent for any filter, so for any code that you will use. So we had to eliminate them. They were usually the same value, but 3 or 4 or 5 times from the same epoch. And we also filtered data that was higher than 3 times the standard deviation of the whole series. I found a paper that said that the Zenith Troposphere Delay was correlated with the station height, and it sounded coherent because of the hydrostatic equilibrium equation. So the bigger the height, the lower the pressure. It should be coherent. So we analyzed our data, at least if it was going to be coherent with this formulation, and it was 92%. So we moved on. And we first did what we called a non-parametric analysis. That means we're not imposing any function or any form to adapt to the data, or the data to adapt to any form. Like, it's not like I want it to be like a cosinus or like an exponential or like a logarithm. No, I leave it free to show me its behavior. So we only averaged for all the same epoch for the same day of year to have an annual behavior. Could see an annual cycle or not. Was this random, or was this behaving like a cosinus, but without imposing it to be a cosinus? This was the first way we did it, and then the same for the piling up from the same epoch for the same DOI, and then for all the DOIs, for all the day of years, to have the diurnal behavior. This was the 2 methodologies we used for analyzing if we could see any cycles. And then, of course, we applied the Fourier transform to see if it was the same as we had seen. So we know there is an annual cycle. We know there is a diurnal cycle. Does the fast Fourier transform see it or not? So we have 2 analyses, the parametric and the not parametric. And well, I'm not going to say the conclusions. So for the annual behavior, for the IGS data we used, in 92% of the analyzed sites, so it was 23 out of 25 analyzed, we saw an annual cycle. In some of them was the smaller the amplitude, and some of them was bigger. In some others was not as clear, but you could still see a curve in the winter, so slower. This is winter for us. So it was not as clear in some of them, but still there was an annual cycle. And this is the amplitude for the whole South America, for the 25 sites, for the 23 sites. 2 of them didn't have any annual behavior for South America. This is the mean amplitude, so it's taken from the red curve here. This is not Fourier. This is non-parametric. So it's the maximum we found after doing all the filters and all the means. And so as it is clear, we see for mid-latitudes from 20 to 4, 35, 40, the annual amplitude is bigger. For bigger latitudes, it's a lot smaller. And for islands, it's a lot smaller too, which it was interesting to see because it does respond to the regional weather at least. And this is the annual cycle with the fast Fourier transform, similar to the one that I showed before. It is clear, the annual cycle that we can see in the delay. I don't know, maybe this green is too clear, but there is a spike there for the cycle. This is what the Fourier transform showed. And for the diurnal cycle, this is the non-parametric analysis. Again, we had some bigger amplitudes, some smaller amplitudes. I'm not going to say conclusions again. And this is the amplitudes for the whole station. I think it was 115 we ended up with. And the results were similar to the annual amplitude. So for mid-latitudes, continental, especially continental and higher altitude, we had bigger amplitudes of the diurnal component as well. And this is analyzing with the Fourier transform. What we did is we looked at the 115 power spectrums, and we said, this one has the component, this one does not have the diurnal component. So it was yes or no. Is there a spike on the day or not? Like, ¿qué pasó? Esto. So do we see or do we not see the spike here? So we have two bags. Yes, no, yes, no, yes, no, for the 115. And this is what we obtained. So there's clearly two regions in Argentina that you do see the diurnal cycle, while you do not see it in the rest. And the regions are very marked. And for all the equatorial regions, we did see the diurnal cycle as well. And this shows that it is not correlated with the latitude, at least, because we have sites for the same latitude where you see or where you do not see. So it's more related to the local weather, to the topography, to the height of the stations. So it's more complicated than saying for mid-latitudes you do see, for higher latitudes you do not see. It's more complicated than that. And, well, the conclusions. So for the non-parametric analysis, we have seen bigger annual amplitudes for mid-latitudes and desert areas. And for latitudes above 40 and humid sites, they were smaller. And the fast Fourier transform for both cycles we analyzed, they show the same as the non-parametric. So it's like validating the Fourier transform, which it was not our aim, but and the most curious result we found is that the diurnal cycle was only focused in some areas. It was no, you couldn't make a general result for latitudes or for height, or whereas for the annual you could. For the diurnal cycle, it's more complicated than that. That's it.
Thank you very much. Now is the questions time. So
I think I have been off the camera the whole time.
Sorry?
I think I have been off the camera
But the micro has been following you.
Okay.
So, yes. Any question from the floor for the audience?
No.
Well, there was a slide where you showed the amplitude depending on the site, not the one, another one before that.
Depending on
The location in South America.
the annual.
No. This one.
Yeah. This is the annual cycle. Yeah.
Do you know why it's this behavior? Because for me, it's like, well, I thought on Appleton country normally in the case of ionosphere, which may be covering as well, maybe Brazil side and all the central part. Yeah, I don't know, Manuel. Maybe you think there is some potential.
Do you? I will repeat your question. Are you asking about any potential correlation or relationship between the?
Maybe there is some possibility that there is correlation.
I don't think so, because in my understanding is the maybe the correlations, because I understand that you have processed this with the ionospheric free combination of GNSS, the final products directly.
Black box.
Okay. So directly from them. So the IIS centers are usually working with ionospheric free combinations, or at least or in equivalent way. So this means that at least 99.9% of the ionospheric effect has been removed, which is.
I mean that the tropospheric behavior would be somehow
related with the dynamo effect. Okay.
Remove ionosphere from the measurement.
Well,
I mean, if the physical processes,
yeah.
at some point could.
I understand that this can be seen very well in occultation, radio occultation data. Both regions are quite disjoint, physically speaking, quite disjoint, because when you start having free electrons at 50 kilometers height or more, and the neutral refractivity is quite small. But coming back to the previous point, you still can have 1 per 1,000 of residual in the tropospheric, or affecting the precise positioning. So this could be a gate, but these effects will be quite small. We have studied these effects in the past. And
yeah. The annual cycle, I think it could have a lot to do with the ionosphere. I mean, at least the amplitudes, they're bigger closer to the equator, so it looks like it can be related, because it's also in the equators.
Maybe they are sharing the higher energy they are receiving from the sun, but my guess is that the physical processes are in general, my guess, disjoint. There are some connections, at least, which are being very interesting connections, like tropospheric warming effects, or for instance, connecting the ionospheric waves with meteorological weather phenomena. So, but this is an open point, of course. Yeah.
I think the annual component, it is related with the sun, because it has an annual cycle, very clear, but the diurnal, not necessarily. No. That's what we found. It was curious for us that it was not that related to the movement of the Earth about the sun. Yeah.
Thank you. results is very interesting, and I want to ask, could you find other data source like meteorology satellite images about the region you studied? I think maybe you could find some correlation between IGS data and other satellite images. Yeah.
Yes, what we did try to do is to have values for the pressure at the same sites, and to analyze if its behavior was correlated to the Zenith Troposphere Delay. But there is not enough data. There's not enough barometers. So we couldn't come to any conclusions. But I have never considered, I don't know, Jason maybe has, I don't know, what other bodies?
Yeah, they have tropospheric products. I am not very aware about that, but yes, they are. I guess they are offering.
Yeah. It is, the phenomena is so local that if your site is 10 kilometers apart from the other data you have, you can't correlate it. Maximum is 10 kilometers. So it's hard to find another source or a different methodology to compare with.
I have another question for you. Do you think that this study could be made more general? So this is very interesting and focused on a very large region of the world. The possibility of extending this approach to a worldwide analysis?
Yes. The only background we found to this work was a paper that did actually that for 120 stations global. But we prefer focusing in one area because the phenomena are so local. So you have to make sure that you have a lot of stations in the same area.
Yes, the statistics.
Yeah.
The significance.
Yeah.
Of the statistical analysis.
Yeah. So if you process global data, there's no point in having one site at 2,000 kilometers from the next site, and there's no conclusion to be made. So actually, this paper has no conclusion.
So in this regard, for instance, the networks of California, South California Dense Network, or the GeoNet in Japan might be suitable to extend this analysis, because these networks, as you know, are originally motivated mostly for the seismicity, also for the weather phenomena, but especially for the seismicity. So this may deserve an extension.
Yeah, if there are a lot of sites together, it's interesting to look at. Yeah. Yeah. Yeah, it would be good to look at that.
I have received one question by me.
Okay.
I can pose it. So I have received a question from Professor Dimitar Usonov. He's professor at Chapman University in California. So he's asking about that in the period, in relation to the influence of large seismic events into the troposphere during the study period, there were at least 3 earthquakes with magnitudes greater than 7 near the area of study, your area of study during the period. Did you find any outliers during the earthquake period, day of week? So be some abnormal values. He provided a list of earthquakes. So maybe we could summarize. It's difficult to answer this in real time, of course, but maybe I can summarize about if you have considered or it might be considered the potential relationships between earthquakes, change in temperature, change in conductivity, change in humidity before the earthquakes. Some theories are strongly suggesting with anomalous variations of the troposphere delay. So just some comment about that.
Before filtering the data, we had so many sites and such longer series that we did not look into one of them. If it was bigger than 3 times the root mean square or the standard deviation, it was out, the value for that epoch. But one colleague of mine, at the same time that I was doing this, she was focusing on earthquakes, but with the height component of the site, not with the troposphere delay. But it would be interesting to have her results compared to mine, or what possibly could be mine.
Yes, maybe this is great, because maybe it might not be too much effort to revisit the outliers or not, to revisit the initial estimates before filtering and trying to look for any potential relationship between outliers regarding to earthquake time and distance to the epicenter. This may be just to take a look in case some potential relationship might be found. Yeah. So, well, I appreciate your answer on behalf of Dimitar as well, Professor Ozanov.
Thank you. Someone else?
Thank you for the presentation. And maybe this is my first time to contact the troposphere. And I have a question about your data set is related to the low latitude and the middle latitude, right? I have a question is, in the middle latitude, is it possible in the middle latitude is more regular phenomenon of the troposphere than the low latitude?
If I understood well, you're asking if the mid latitudes have a more regular behavior. For the annual component, yes, you do expect bigger annual oscillations, because we have the 4 seasons in mid latitudes stronger than in the equator or the poles. So they mostly do, the stations. It's only 25 stations. It's not very much. For the troposphere, in such a large area, it is not a lot of data to come to any conclusions. But still, the mid latitudes do respond to what you would expect them to do, except for the northeast of Brazil, and it's closer to, so it should be a lot smaller because it's closer to the ocean, so the amplitude should not be that big, and also it has very low latitude, so again it should be smaller, because we know there's no much change in the equator between summer and winter, so the amplitude should not be that big. But that may respond to very, very dry winds that come, I don't know, this is meteorology. I'm not an expert. And I asked 3 meteorologists, and the 3 of them said that the behavior of the weather there, it's very chaotic. It doesn't have a pattern. And it responds to very dry loss, like very low humidity loss, and it's closer to the ocean. It's close to the ocean. It has low latitude, so it shouldn't. They said something about mesospheric winds. and I stopped asking. I mean, they didn't have an answer. So that is, these 3 stations here respond to local weather. Did I answer your question? No, yeah.
Because I process the Japanese data, it's in the middle latitude with in the high density of the receiver distribution. Maybe for the troposphere research, maybe give I don't know if can be give a high resolution of the troposphere distribution. I don't know. Maybe can have a better to this phenomenon research because with lots of the receivers distribution in Japan with more than yes something like that. Mm.
We have access to the data. Han knows very well about this data.
Thank you.
Thank you. Any other question? I check. Okay. So, so in such a case, unless you have any other comment or question, just to thanks again, sorry, to Victoria for the presentation. So thanks so much, and in this way we finish the talk.
Thank you. Thank you, everyone.